Our cosmic story begins with absolute nothingness, not empty space, but a profound and total darkness. For millions of years after its explosive birth, our universe existed without a single point of light. No stars, no galaxies, not even the faintest glow to break the endless night. This was the cosmic dark ages, a silent epoch that holds the key to everything we are. By the end of this journey, you will understand the incredible sequence of events that built a lit cosmos from pure shadow. How did a formless sea of gas become the cradle for the very first suns? What strange physics governed a world without any elements heavier than helium? We are about to trace the universe's first steps out of the void. What does it mean that our entire reality was born from such profound darkness? To find the source of light, we must first understand the nature of that initial darkness. Picture the universe not as a void, but as a blinding, seething ocean of pure energy. In the first few moments after its birth, the cosmos was unimaginably hot and dense, a churning plasma of fundamental particles. Protons and neutrons, the future building blocks of atoms, were swimming in a sea of light, constantly slammed apart by the sheer intensity of the radiation around them. This was a state of matter so extreme that even the simplest atoms were impossible. It was a true primordial soup, a cosmic broth where everything was broken down to its most basic ingredients, constantly colliding and recombining in a frantic dance. In this superheated environment, light itself was trapped. Countless particles of light, called photons, filled every corner of space, but they could not travel freely. The universe was filled with free electrons, particles with a negative charge, and these electrons acted like tiny, perfect mirrors. Every time a photon tried to move, it would immediately crash into an electron and scatter in a new direction. This happened over and over, trillions upon trillions of times. The result was a cosmos that was completely opaque. If you could somehow have been there, you would have seen nothing but a uniform, featureless glow in every direction, a fog of light so thick it was like being inside the heart of a star. For nearly 400,000 years, this was the state of our entire reality, a hot, dense, glowing fog where no structure could persist and no light could escape to show us what was happening inside. This opaque plasma is the blank canvas upon which the first stars would eventually be painted. But before that could happen, the universe had to undergo a profound and necessary cooling. But that hot, glowing fog did not simply appear out of nowhere. Its very existence and the potential for a structured universe within it was set by an event of almost impossible power in the very first moments of time. To understand the canvas, we must understand the artist's first decisive brushstroke. This is the story of cosmic inflation. In the tiniest fraction of a second after the universe began, something extraordinary happened. Space itself underwent a period of hyper-accelerated expansion, ballooning from a size smaller than a single proton to something far larger than our entire observable cosmos today. All of this occurred in less time than it takes for light to cross the width of an atom. This was not an explosion into space, but a staggering expansion of space itself. The consequences of this brief, unimaginable event are the foundation for everything that followed. First, inflation acted like a cosmic iron, smoothing out any major wrinkles or irregularities in the fabric of the newborn universe. It gave the cosmos the remarkably uniform, flat geometry we observe in the cosmic microwave background, that afterglow of the hot plasma we just described. But inflation did something even more profound. In that seething quantum foam of the earliest universe, tiny fluctuations were inevitable. Particles and energy would pop in and out of existence on the smallest scales, a natural jitter inherent to reality itself. As space inflated at a phenomenal rate, it stretched these microscopic quantum ripples to astronomical sizes. imagine a tiny, nearly imperceptible wrinkle on the surface of a deflated balloon. Now imagine inflating that balloon to the size of a planet. That tiny wrinkle becomes a vast, continent-sized ridge. Inflation did exactly this to the fabric of the universe. Those stretched quantum ripples became slight variations in density. Some regions of space were ever so slightly denser with matter and energy than others. These are the primordial seeds. They are the raw material for all structure in the cosmos. Every galaxy cluster, every swirling galaxy, every star and planet that would ever form owes its ultimate origin to these microscopic imperfections, magnified to a cosmic scale by that initial, violent stretching of space. Without inflation, smoothing, and seeding, the universe might have remained a perfectly uniform, featureless soup forever. There would have been no gathering points, no gravitational wells to collect the gas of the dark ages. The cosmos would have been a true void, silent and unchanging for all eternity. But because of those tiny, stretched ripples, the universe was gifted with a blueprint, a faint fingerprint of things to come written into the very fabric of space. But that violent expansion had to end. As inflation's incredible engine wound down, all that stretched energy was released, flooding the newborn cosmos with a seething ocean of particles and radiation. The universe was now a nearly uniform broth of quarks, gluons, and photons, a superheated plasma so dense that nothing could hold together. For the next several minutes, a critical transformation would unfold, one that would set the chemical fate of the cosmos. This is the era of Big Bang Nucleosynthesis, the universe's first and most fundamental act of creation. As the cosmos expanded, it cooled with breathtaking speed. Within the first second, protons and neutrons, the cores of future atoms, had frozen out of the energy soup. For a brief window, they were in balance. But protons are slightly lighter than neutrons, and in the high-energy collisions of the early universe, that tiny difference mattered. Free neutrons are unstable and will decay if left alone, turning into a proton. As the temperature plummeted, the scales tipped. By the time the universe was just 1 second old, for every 7 protons, there was only 1 neutron left. This ratio was now locked in, a cosmic decree written by the laws of physics and the speed of the cooling. Then, around the 3-minute mark, the temperature fell to about 1 billion degrees. This was the magic threshold. The universe was finally cool enough, and yet still dense enough, for nuclear fusion to begin. Protons and neutrons could now collide and stick together, overcoming their natural electrical repulsion. It was a frantic, universal alchemy. A single proton and neutron fused to form deuterium, a heavy form of hydrogen. Before these new deuterium nuclei could be blasted apart again, they quickly captured more protons and neutrons. Almost immediately, these small clusters fused into the next stable structure, the nucleus of helium, which contains 2 protons and 2 neutrons. For about 17 minutes, the entire cosmos was a nuclear furnace, fusing the available neutrons into helium. And then, just as suddenly as it began, it was over. The universe had expanded and thinned so much that particles were now too far apart to collide with any meaningful frequency. The great fusion engine shut down. The result was a cosmic chemistry set with only 3 elements. Roughly 75% of the ordinary matter by mass was hydrogen, single protons that would become the fuel for stars. Nearly 25% was helium, the ash of that first great burning, and a vanishingly tiny trace, less than 1 part in a billion, was lithium. Nothing heavier was forged, no carbon for life, no oxygen for water, no iron for planets. The universe had created the raw fuel, but the work was far from done. For the next vital step, atoms themselves needed to form, and that would require the universe to grow much, much colder and darker first. But the universe was still far too hot for those newly minted nuclei to capture electrons. For nearly 400,000 years, the cosmic drama was one of relentless, chaotic scattering. The universe remained a thick, opaque plasma, a roiling sea where protons, helium nuclei, and free electrons were constantly buffeted by an overwhelming tide of light. Every photon, every particle of light, was like a tiny, energetic bullet, smashing into electrons and keeping them perpetually unbound from the atomic nuclei that would one day anchor them. It was a standoff between the irresistible force of light and the nascent pull of atomic structure, and for all that time, light was winning. The cosmos was a blinding, featureless glow in every direction, a prison of pure radiance where nothing could hide and nothing could take shape. But the universe was expanding, and expansion brings a profound and inevitable change, cooling. As space stretched, the energy within it was diluted. The frantic photons lost their punch, their wavelengths stretched by the expanding fabric of reality itself. Their energy slowly, steadily diminished. And then, around 380,000 years after the beginning, a critical threshold was crossed. The universe cooled to a temperature of about 3,000 Kelvin, roughly half the surface temperature of our Sun today. At this point, something monumental happened. The photons no longer carried enough energy to keep electrons free. Suddenly and universally, the long dance of scattering came to an end. Electrons, drawn by their opposite electrical charge, were finally captured by the waiting nuclei. Hydrogen nuclei, single protons, each grabbed an electron to become a complete, neutral hydrogen atom. Helium nuclei captured 2 electrons each. For the first time in cosmic history, stable, neutral atoms existed. This pivotal event is called recombination, though it's a bit of a misnomer, as the particles were combining for the very first time. Its consequence was immediate and breathtaking. With the electrons now bound securely inside atoms, the cosmic fog lifted. The countless photons, which had been trapped in a constant game of pinball with free electrons, were suddenly set free. For the first time, light could travel across the universe in a straight line without obstruction. In an instant, the opaque, glowing plasma became transparent. That primordial flash of liberated light, stretched and cooled by 14 billion years of cosmic expansion, is what we detect today as the cosmic microwave background. It is the oldest picture we can ever see, a baby photo of the universe at the moment of its own transparency. But this newly clear cosmos came with a cost. The release of that light drained the universe of its primary energy source. With the photons no longer trapped, they streamed away into the expanding darkness, their energy fading with each passing moment. The universe did not just become transparent, it became profoundly, utterly dark. The brilliant glow of the plasma faded to black, and the cosmos entered its long, silent night. The era of structure could finally begin, but it would have to build itself in near-total darkness, guided only by the faint gravitational whisper of those ancient density seeds. That first true darkness settled over everything. For millions of years, the universe did nothing but grow larger, colder, and quieter. With the last glow of its birth now streaming away as the cosmic microwave background, the cosmos was left with a profound and simple emptiness. All the ordinary matter in existence was now in the form of neutral hydrogen and helium gas, a thin, nearly perfect mist spread evenly across an expanding void. There were no stars to ignite it, no galaxies to give it shape. If you could have floated in that epoch, you would have experienced a silence deeper than any on Earth, and a darkness so complete it would have been absolute. The only light came from that fading afterglow, which itself was shifting from visible warmth into invisible microwaves, a whisper of heat against the deepening cold. This was not a static emptiness, however. Remember those primordial seeds, the density ripples imprinted by inflation. They were still there, woven into the fabric of this gaseous sea. Certain regions, through random chance amplified over eons, held just a tiny fraction more matter than their surroundings. and in the utter absence of any competing energy, the slow, patient force of gravity finally had its chance to work. But gravity is weak, and the universe was vast and expanding, pulling everything apart. So for an achingly long time, nothing seemed to happen. The gas simply drifted, cooling further as space stretched. This was the cosmic dark ages in its purest form, a universe of potential waiting in the dark, its entire future written in faint variations of a featureless fog, with no beacon yet to signal that the long night would ever end. Yet within that perfect darkness lay a hidden blueprint. Those faint density ripples, stretched to cosmic proportions by inflation, were now frozen into the distribution of the primordial gas. They were the universe's only landmarks in a sea of uniformity. In regions where the gas was ever so slightly denser, gravity exerted a subtly stronger pull. This is the quiet, relentless engine that would build a cosmos from nothing. Imagine the gentlest of slopes on an endless, flat plain. A single pebble placed there would not move, but a slow, steady rain of fine dust would, over eons, begin to drift downhill, gathering where the slope is deepest. The universe, in its dark ages, was experiencing a rain of atoms. Hydrogen and helium atoms, adrift in the expanding void, felt the faint tug of these gravitational slopes, the overdensities. They began an imperceptible drift toward the denser patches. This was not a sudden collapse, but a slow, cosmic accumulation. As more atoms gathered, the gravitational pull of that region grew stronger, which in turn attracted more atoms from a slightly wider area. It was a positive feedback loop of breathtaking patience, operating on timescales of millions of years. These gathering clouds, these slight concentrations in the fog, were the absolute cradles of all future structure. Within their deepening gravitational wells, the gas was beginning to compress, ever so slowly. The atoms within these clouds started to bump into each other more frequently. And with every collision, a tiny amount of the gas's gravitational energy was converted into heat. These were the first warm spots in a cold, dark universe, not yet stars, but the glowing embers that would one day ignite them. The long night was not empty, it was purposeful. Every galaxy supercluster, every spiral arm, every planet that would ever host life was, at this moment, represented by nothing more than a diffuse, slowly tightening knot of hydrogen and helium, waiting in the dark for its moment to shine. But gravity alone was not the only architect at work in that ancient dark. There was another, invisible force shaping the destiny of the primordial gas, a mysterious presence that never once felt the touch of light. This is the story of dark matter, the hidden skeleton of our cosmos. While the ordinary hydrogen and helium atoms were constantly buffeted by radiation pressure in the early universe, dark matter particles were fundamentally different. They do not interact with light at all. They are ghostly, passing through photons and through each other as if they were not even there. This meant that when the cosmic plasma was a blinding, opaque fog, dark matter was already moving in the shadows. It felt only gravity, and so, while ordinary matter was trapped in that hot, scattered soup, dark matter began to quietly, invisibly, clump together under its own gravitational pull. It started gathering around those primordial density seeds long before the atoms could. These growing clumps of dark matter formed the first true structures in the universe, vast, diffuse halos of an unknown substance. They were not stars or galaxies, but immense, invisible gravitational anchors. Think of them as the deep foundations of a city, laid down in bedrock long before the first brick is ever placed. When the universe finally became transparent and the ordinary gas was set free to drift in the darkness, it did not drift aimlessly. It flowed directly into the gravitational wells carved out by these waiting dark matter halos. The dark matter had done the hard work of creating the initial framework, the deep valleys in the fabric of space where matter would naturally pool. This invisible scaffolding dramatically accelerated everything. The hydrogen and helium gas now had a clear destination, a pre-existing slope to slide down. Without dark matter's head start, the gentle pull of gravity on the gas alone might have taken far, far longer to build the first structures, perhaps so long that stars might never have ignited at all. But with these ready-made gravitational traps in place, the ordinary matter had a blueprint to follow. The gas began to accumulate in earnest at the hearts of these dark halos, compressing, swirling, and growing hotter. The Dark Ages were ending not with a single event, but with the silent convergence of two cosmic ingredients, the visible gas we are made of, flowing into the invisible embrace of a mystery we still strive to understand. This partnership between the seen and the unseen was the final, critical step. The stage was now set. All that was needed was for the gas at the center of these gathering storms to reach a point of no return. Deep within those gathering knots of gas, a silent battle of titanic forces was beginning. The cloud's own gravity pulled everything inward with an increasing, relentless grip. But as the gas compressed, its atoms were forced closer together, colliding more and more frequently. Each collision generated heat, and that heat created an outward pressure, a force pushing back against the crush of gravity. For a long time, this was a perfect stalemate. The cloud could shrink no further, held in a fragile equilibrium by this internal thermal support. It was a cosmic balancing act, and to tip the scales, the cloud had to do something counterintuitive. It had to cool down. To collapse into a star, the gas needed to shed that heat, to radiate its thermal energy away into the cold, dark space around it. Only by losing energy could the pressure drop enough for gravity to win and pull the cloud into a denser, hotter core. This process of cooling, however, presented the first stars with a unique and profound challenge. Our universe was chemically primitive. This gas was made of only hydrogen and helium, the simplest elements, and these simple atoms are terribly inefficient at cooling. In a modern star-forming cloud, dust grains and molecules like carbon monoxide act as brilliant radiators. They absorb the cloud's heat and re-emit it as infrared light, which escapes easily into space, allowing the cloud to contract rapidly. But the first clouds had none of that. No dust, no complex molecules. Their only way to cool was through a slow, clumsy process involving the hydrogen atoms themselves. Occasionally, two hydrogen atoms would collide and briefly form a fragile hydrogen molecule before breaking apart. In that fleeting instant, they could release a tiny packet of energy as infrared light. It was an agonizingly slow leak, not a rapid release. This fundamental difference in chemistry meant the first protostellar clouds could not shed heat quickly. They were like a poorly insulated engine running hot and struggling to cool. This slow cooling had a direct and dramatic consequence on their fate. Because the pressure stayed high for longer, the clouds had to become incredibly massive before gravity could finally overcome it and trigger a true collapse. They could not fragment easily into many small clumps like modern clouds do. Instead, they collapsed as single, monstrous entities, gathering hundreds of times the mass of our Sun into one swirling, chaotic maelstrom. The physics was simple, but the outcome was extraordinary. The very poverty of the early universe, its lack of complex chemistry, forced it to build its first beacons on a scale we can scarcely comprehend. This slow leak of energy had a name, and it was the most important molecule in the young cosmos, molecular hydrogen. In a universe devoid of any other coolant, these fragile pairs of hydrogen atoms were the universe's first and only refrigeration system. Their formation was a story of sheer persistence. The process began with the tiny fraction of free electrons that remained after recombination, zipping through the dark. When one of these electrons collided with a neutral hydrogen atom, it could briefly knock it into an excited state. In that fleeting, energized moment, the hydrogen atom could stick to another, forming the delicate bond of a hydrogen molecule. It was a rare three-body dance in an almost empty void, but over millions of years it happened just enough. Trace amounts of this molecular hydrogen began to accumulate within the deepest, densest parts of the gas clouds. And this molecule, simple as it was, possessed a superpower that single atoms lacked. It could rotate and vibrate. Think of a single hydrogen atom as a still, silent marble. A hydrogen molecule is like a tiny dumbbell. It can spin and it can wobble, and according to the laws of quantum physics, these rotations and vibrations can only happen at specific, discrete energies. When the molecule shifts from a higher energy spin or vibration to a lower one, it must release the difference. It does so by emitting a photon of infrared light. This was the breakthrough. While atomic hydrogen could only cool through clumsy collisions, molecular hydrogen could radiate heat away with a precise, efficient mechanism. Each tiny infrared photon carried a packet of the cloud's thermal energy out into the cold, dark space. It was as if the gas cloud had finally developed pores through which it could sweat. This gradual cooling was the final, critical trigger. As the cloud's core shed heat, the internal pressure dropped. The stalemate between pressure and gravity was broken. Gravity could now compress the gas further, which made it denser and hotter, which in turn created more molecular hydrogen, leading to more cooling, a runaway cycle of collapse. But here is the beautiful consequence. This cooling did not cause the entire massive cloud to crumple into a single point all at once. Instead, the ability to radiate energy allowed different regions within the swirling maelstrom to cool and condense at slightly different rates. Cloud began to fragment. Smaller, denser knots started to pull themselves apart from the larger whole. The first star-forming clumps were being born inside these monstrous gaseous wombs. Molecular hydrogen, a trace impurity in a sea of atomic gas, had provided the release valve. By enabling the cloud to cool, it allowed gravity to not just win, but to sculpt. The universe was no longer just gathering matter. It was beginning to carve it into distinct, destined pieces. The long, silent preparation was over. Deep within these fragmenting knots, temperatures and densities were now rising toward a point humanity would later call ignition. Deep within those fragmenting knots, the temperature was climbing past 10,000 degrees. These were no longer just clouds of gas, but the first protostellar cores, embryonic suns taking shape in the universal dark. Each core was a gravitational trap of its own, a dense, hot seed at the center of a swirling vortex of primordial material. And from that moment, a violent feast began. The surrounding gas, still falling inward from the massive parent cloud, began to rain down upon these newborn knots in a torrential downpour of matter. This was the era of accretion, a process of cosmic consumption that would define the character of the very first stars. For thousands of years, perhaps even tens of thousands, these protostars gorged themselves. Vast rivers of hydrogen and helium spiraled in from the surrounding disk, slamming into the growing core with tremendous energy. Each impact released a flash of heat, and the temperature at the very center began a steep, relentless climb. The core was not yet a star, not in the sense we understand. It was a seething, opaque ball of plasma, glowing a dull red from the sheer violence of the infall. It grew in mass and density not from internal power, but from the constant bombardment of material from its celestial womb. This was a star being built from the outside in, layer by furious layer. The physics of this accretion was chaotic and inefficient. Not all the falling gas made it directly to the surface. Much of it swirled into a vast, hot disk around the protostar, a turbulent maelstrom where material clashed and collided before finally finding its way down the gravitational drain. This disk was the crucible where future solar systems might one day form, though for these first stars, that potential would remain tragically unfulfilled. The sheer scale of the feast was staggering, because the parent cloud was so massive and had so little ability to fragment. The accretion onto each core was prodigious. These protostars were not just gathering the mass of a sun like our own, they were on a path to become true behemoths, giants 100 times heavier or more. All the while, the heart of the core grew hotter and denser, compressed by the incredible weight of its own growing body. The atoms within were squeezed together so tightly they could no longer maintain their independence. Electrons were stripped from their nuclei, creating that familiar seething plasma. But this time, the plasma was not a uniform cosmic fog. It was a tightly packed, intensely hot sphere, buried deep within its own swirling construction site. The pressure at the center became unimaginable, and as the temperature passed the critical threshold of about 10 million degrees, the universe stood at the brink of a revolution. Within that searing heart, protons, the nuclei of hydrogen atoms, were moving with such frantic energy that they could finally overcome their natural electrical repulsion. They were about to touch, to fuse, and in doing so, to unlock the energy that had been bound within matter since the dawn of time. The long cosmic night was seconds away from its end. The moment of ignition was not a gentle flicker. Deep within that searing core, where temperatures soared past 10 million degrees, protons achieved the impossible. They overcame their mutual electrical repulsion and fused together, forging deuterium and then helium in a runaway chain reaction. Nuclear fire awoke in the universe for the first time since its own explosive birth. This was the birth of a star, but not a star like any we know today. Astronomers classify this first, primordial generation with a special designation, population 3 stars. They were the true pioneers, and their character was shaped entirely by the pure, primitive cosmos that created them. Their most defining feature was their staggering scale. Unburdened by the complex chemistry that allows modern clouds to fragment, these stars grew by consuming the vast reservoirs of their parent clouds. They likely formed as true behemoths, with masses ranging from 100 to several hundred times that of our own Sun. Picture our Sun, a stable yellow dwarf. Now imagine a sphere of pure hydrogen and helium so vast that you could fit 100 of our suns inside it. That was a typical population 3 star, a leviathan of light. This immense size dictated everything else about them. With such enormous mass crushing down on their cores, the internal pressure and temperature were correspondingly extreme. Their surfaces would have blazed with a fierce blue-white fury, many times hotter than our Sun. They were not the gentle, life-giving furnaces we orbit, but searing, ultraviolet ovens pouring out torrents of high-energy radiation. Their composition was their purity and their limitation. Made of only hydrogen and helium, they lacked the heavier elements that act as a thermostat in later stars. This meant they burned their fuel with a frantic, unrestrained intensity. There was no slow, steady fusion process lasting billions of years. For a star of such monstrous mass, the battle between outward radiation pressure and inward gravitational pull is a desperate, short-lived affair. They lived fast and died young. A star like our Sun has a projected lifespan of about 10 billion years, a period of stability that allowed for the gradual development of a planetary system and on one world life. A population 3 star had no such luxury. Its brilliant, violent existence might have lasted only a few million years, a cosmic blink of an eye. In that brief, spectacular flash, they consumed their entire nuclear fuel at a prodigious rate, racing toward an inevitable and catastrophic conclusion. They were not built for longevity, but for transformation. Their entire purpose, written into their physics, was to burn brightly, change the universe around them, and then perish in a manner that would forever alter the chemical destiny of the cosmos. Their brilliant ultraviolet light did more than simply pierce the universal dark. It began a process of profound change in the very environment that had created them. This is the story of astrophysical feedback, the universe's first attempt at self-regulation. the radiation pouring from those massive population 3 stars was not the gentle, visible light we see from our sun. It was a torrent of high-energy ultraviolet photons, each one carrying enough punch to rip an electron away from a hydrogen atom. This process is called ionization, and it turned the serene, neutral hydrogen gas surrounding these first stars back into a seething plasma of charged particles. Imagine the star as a blazing campfire in a cold, damp forest. The intense heat from the fire does not just light up the immediate area, it dries out the wet leaves and wood around it, changing the very conditions that would allow another fire to start easily nearby. The first stars were doing exactly this on a cosmic scale. Their radiation carved out vast, growing bubbles of ionized hydrogen in the primordial fog. Inside these bubbles, the gas was no longer cool and neutral. It was hot, charged, and turbulent. This reheating of the gas had a critical consequence. Remember, for a new star to form, a cloud of gas must be able to cool and collapse. Heat creates pressure, and pressure resists gravity's pull. By flooding their surroundings with energetic radiation, the first stars were essentially pumping the brakes on further star formation in their own neighborhoods. They were raising the temperature and pressure of the raw material, making it too puffy and energetic to easily condense into new gravitational seeds. This radiative feedback was the universe's first balancing act. The very act of creation began to limit further creation in the immediate vicinity. It was a paradoxical outcome. These luminous pioneers, born from the cold dark, were now actively working to ensure that their own kind might not easily arise again next door. They were sculpting their legacy into the cosmos, not just with light, but by altering the fundamental state of the matter from which future generations would be built. Their brilliant but brief lives could only end in one way. A star of such immense mass, born from pure hydrogen and helium, faces a terminal physics that is both elegant and terrifying. When the core of a population 3 star finally exhausts its supply of helium, the balance of power within it shatters completely. For millions of years, the outward push of radiation from fusion had held the crushing weight of the star's own outer layers at bay. But now, with the core's energy source spent, that support vanishes. Gravity wins its long war in an instant. The core collapses with catastrophic speed. In stars like our Sun, this collapse is eventually halted by quantum forces, leading to a less violent end. But for these first giants, the core temperatures become so phenomenally high that something bizarre happens. The heat energy itself begins to spontaneously create matter. In the heart of the collapse, photons of light, which are pure energy, are converted into pairs of electrons and their antimatter counterparts, positrons. This process, called pair production, siphons away the thermal pressure that was the last line of defense against gravity. It is as if the floor of a burning building suddenly turned to air. With that final pressure gone, nothing can stop the collapse. The entire core implodes, and in a final, defiant rebound, the star does not just explode. It is utterly, completely annihilated. This is a pair instability supernova, a detonation of such raw power that it leaves behind no remnant, no black hole, no neutron star. The entire stellar mass, hundreds of times that of our Sun, is blasted into the void. The energy released is almost beyond comprehension. For a few weeks, this single dying star can outshine its entire nascent galaxy, a final, furious beacon in the dark. But the true legacy of this cataclysm is not the light, but the cargo it carries. Within that titanic blast wave are the first complex atoms the universe has ever known. The star, in its life and death, had acted as a cosmic forge. Through successive stages of fusion in its core, it had cooked the primordial hydrogen and helium into heavier elements. Carbon, the backbone of life, oxygen, essential for water and breath, neon, magnesium, silicon, and all the way up to iron. these elements, forged under extreme pressure and temperature over the star's short life, were now violently ejected. They were seeds of a new kind of chemistry, scattered like precious dust across the pristine hydrogen and helium of interstellar space. This was the universe's first act of enrichment. Before this moment, every gas cloud, every potential new star was made of only the two simplest elements. Now, for the first time, there was pollution, a beautiful, fertile pollution. Microscopic grains of solid material, atoms that could link into molecules and form dust, were injected into the cosmos. The death of one star forever changed the raw ingredients available for all stars to come. The pure, monotonous universe of the Dark Ages was gone. In its place was a cosmos subtly laced with the ash of its first pioneers, a testament written not in light, but in the newly forged elements that would one day become planets, oceans, and us. That scattered stardust was the universe's first true inheritance. With those first titanic explosions, the cosmic chemistry set was no longer limited to just two simple elements. Astronomers call all elements heavier than helium metals, a broad term that includes everything from carbon to iron. This metallic ash, ejected at nearly the speed of light from the dying population 3 stars, began a slow but irreversible process of cosmic pollution. It mixed with the vast, pristine reservoirs of hydrogen and helium, seeding the darkness with the potential for everything to come. This enrichment was not uniform or instant. It happened in pockets and bubbles around the sites of those first supernovae, creating a patchwork universe where some regions remained pure and others became subtly, fundamentally changed. The presence of even a tiny trace of these new elements altered the physics of star formation forever. The most critical change was in cooling. Remember how the first stars struggled to form because pure hydrogen and helium are poor at radiating away heat. Metals solved that problem brilliantly. Elements like carbon, oxygen, and silicon can form solid microscopic grains, cosmic dust, and these dust grains are phenomenal radiators. They absorb the thermal energy of a collapsing gas cloud and re-emit it efficiently as infrared light, which escapes easily into the cold of space. It is like comparing a steam engine with a leaky radiator to a modern car with a highly efficient cooling system. The gas could now shed heat rapidly, allowing gravity to overcome pressure much more easily and at lower densities. This one change in chemistry rewrote the rules. Gas clouds no longer had to be monstrous to collapse. They could fragment into many smaller, denser clumps. The era of the solitary behemoth was over. From this newly enriched gas, a second generation of stars was born. These are known as population 2 stars, and they were fundamentally different from their colossal predecessors. With efficient cooling from dust and metals, they formed at much smaller masses, many similar in size to our own Sun. They also contained a faint but crucial metallic fingerprint, a chemical memory of those first catastrophic explosions. Because they were less massive, the internal pressures in their cores were lower. They burned their nuclear fuel at a more moderate, stable pace. Their lives were not measured in mere millions of years, but in billions. This longevity was a gift to the future of the cosmos. A star that shines steadily for 10 billion years provides a stable home for the complex processes of planetary formation and potentially the slow, gradual chemistry of life. But the legacy of that first metallic pollution goes even deeper. Within the swirling disks of gas and dust around these new, smaller stars, those heavy elements could finally clump together. Dust grains collided and stuck, forming pebbles, then rocks, then planetesimals. The iron from a supernova core could become the heart of a rocky world. The oxygen could bind with hydrogen to form water molecules. The carbon could chain into complex organic compounds. Every planet, every asteroid, every ocean is made possible because those first stars lived fast, died violently, and recycled their essence back into the universe. We are not just made of stardust, We are made of the specific stardust forged in the deaths of the very first suns, a legacy of transformation written into the atoms of our own bodies. The dark, simple universe was gone. In its place was a cosmos growing rich with complexity, all because the first light chose to go out in the most spectacular way possible. That final, brilliant flash of the first stars did more than seed the cosmos with new elements. It began a process that would fundamentally change the nature of the universe itself, a billion-year transition from darkness to light called the Epoch of Reionization. The name sounds complex, but the concept is a powerful echo of an earlier time. Remember when the universe first became transparent, when electrons bonded to nuclei to form neutral atoms? That event was called recombination. Reionization is, in a sense, its reverse. The fierce ultraviolet radiation pouring from those first massive stars, and later the earliest galaxies, acted like a cosmic blowtorch. Each high-energy photon carried enough punch to strike a neutral hydrogen atom and rip its electron clean away. This process of ionization began to undo the quiet, neutral state that had characterized the cosmic dark ages. But this time, the transformation was not instantaneous and universal. It was a slow, creeping frontier of change. Imagine a vast, dark forest where someone lights a single torch. That torch illuminates a small clearing. Then another torch is lit nearby, and another. Slowly, individual bubbles of light begin to grow and push back the dark, eventually merging into a widespread glow. This is precisely what happened across the cosmos. Around each luminous source, each brilliant population, three-star or gathering of stars in a proto-galaxy, a growing bubble of ionized hydrogen would form. Within these bubbles, the gas was once again a hot, transparent plasma, just as it had been in the universe's infancy. But outside the bubbles, the vast intergalactic medium remained a cold, neutral fog. For hundreds of millions of years, this patchwork persisted. The universe was a mosaic of light and shadow, with islands of searing transparency expanding into a sea of primordial darkness. This was not a gentle process. It was the universe's great awakening, driven by the relentless output of its first generations of luminous objects, fundamentally altering the medium through which light could travel and setting the stage for the cosmos we observe today. This cosmic dawn did not arrive with a sudden sunrise. It was a slow, hesitant lightening of the universal sky, a gradual retreat of the long night that had lasted for hundreds of millions of years. Those first brilliant bubbles of ionized gas were the initial cracks in the darkness, but they were isolated, lonely beacons in an overwhelmingly black expanse. Yet each one was a seed of change. Around the sites of the first supernova, enriched gas began to cool and collapse once more, but this time under the new rules. The presence of metals allowed for more efficient star formation, leading to the birth of not just individual stars, but the first loose clusters of them, protogalaxies. These were not the majestic spirals we know today, but fuzzy, irregular blobs of a few million stars, held together by their shared dark matter halo. Each of these blobs ignited its own growing bubble of ionized light. The universe was no longer a simple, uniform sea. It was becoming a complex tapestry, a three-dimensional web of dark matter filaments where these luminous knots began to gather at the intersections. The darkness was being pushed back from countless directions at once. The bubbles grew, their edges touching and merging, like the first raindrops on a windowpane slowly coalescing into streams. This was the end of the Dark Ages, not marked by a specific date, but by this profound and irreversible transition. The universe was waking up, and its first act of consciousness was to structure itself. The simple, two-ingredient cosmos was gone. In its place was a dynamic, evolving entity, where light could travel freely through vast, transparent regions, illuminating the grand architecture of matter itself. This cosmic dawn set the physical and chemical stage for everything that would follow. With a structured universe filled with enriched gas, the long, patient work of galaxy assembly could truly begin, building from these modest glowing knots into the colossal cities of stars we see today. The age of pure darkness was over. The universe had learned how to make light, and it would spend the rest of its existence learning what to build with it. Yet we have never directly seen one of these cosmic pioneers. The very stars that ended the universal night remain hidden from our sight, their light stretched and faded by the immense journey across time and space. They are simply too far away, their glow too faint for even our most powerful telescopes to pick out as individual points of light. We are trying to listen to a whisper from the edge of time, a signal that has been traveling for over 13 billion years. So how can we possibly know their story? Astronomers have become cosmic detectives, piecing together the history of the first stars not by looking at them, but by studying the profound shadows and echoes they left behind. The primary method is akin to studying the imprint of a long-vanished animal in ancient rock. Instead of searching for the stars themselves, we search for their impact on the environment around them. The most significant clue comes from that great transition from darkness to light, the Epoch of Reionization. By observing the most distant quasars, brilliant beacons powered by supermassive black holes in early galaxies, we can analyze the light that has passed through the primordial gas on its way to us. If that intervening gas is still neutral hydrogen, it will absorb specific wavelengths of the quasar's light, creating a distinct pattern of dark lines in the spectrum. But as the first stars and galaxies ionized the universe, these absorption lines begin to disappear. By measuring how much of this absorption is present in quasars at different distances, and therefore different look-back times, we can map how reionization progressed. It is like watching the fog lift in slow motion across the cosmos, giving us a timeline for when those first luminous sources must have switched on. Another ingenious approach listens not for light, but for a faint radio signal from the hydrogen gas itself. Before the first stars lit up, the neutral hydrogen that filled the universe emitted a characteristic radio whisper at a wavelength of about 21 centimeters. The expansion of the universe has stretched that signal now into meters-long waves. Ambitious radio telescope projects are trying to detect this incredibly faint echo from the dark ages. Finding it would give us a direct snapshot of the universe before the first starlight, and any distortion in that signal would reveal the precise moment when the first stars began to heat and ionize the gas around them. It is the ultimate cold case where the crime scene is the entire cosmos and the evidence is written in the fading afterglow of creation itself. But perhaps the most profound fossil record of that great awakening is etched into the light from the universe's infancy itself. The cosmic microwave background, that ancient afterglow from the moment atoms first formed, carries more than just a temperature map. It holds within its subtle patterns a direct imprint of the universe's later reionization. When the first stars and galaxies began flooding the cosmos with ultraviolet light, that energetic radiation did more than just ionize hydrogen atoms. It also left a unique signature on the journey of the cosmic microwave background photons, as these ancient particles of light, which had been traveling freely for hundreds of millions of years, finally encountered the newly freed electrons in the ionized bubbles. Something subtle happened. The electrons scattered the light one last time, a final interaction that left a faint but measurable mark on the light's polarization. Polarization is essentially the orientation of a light wave's vibration. You can think of the original cosmic microwave background light as having a very specific, random pattern of these orientations, imprinted by the density ripples of the early universe. When that light was rescattered by electrons during reionization, it gained a new, larger-scale pattern of polarization, like a gentle swirl superimposed on an older texture. By using incredibly sensitive space-based telescopes to measure not just the temperature of the cosmic microwave background, but the precise patterns of its polarization, cosmologists can perform a kind of cosmic archaeology. They can detect that rescattering signal. The strength and scale of this polarization tell a clear story. It reveals the total number of free electrons the light encountered along its path, which directly correlates to how much of the universe had been reionized by a certain time. This allows scientists to essentially date the Epoch of Reionization. Current measurements suggest this global process was about halfway complete when the universe was roughly 550 million years old and was largely finished by the time it reached 1 billion years. This timeline is a critical clue. It tells us that the first luminous sources, those population 3 stars and their early galactic successors, must have begun shining powerfully enough to start this transformation even earlier, perhaps only 200 million years after the Big Bang. The cosmic microwave background, a snapshot from a time long before stars, thus carries within it the ghostly fingerprint of the very first light that ever broke the darkness. It is a message in a bottle sent from the dawn of time, telling the story of its own later illumination. This ancient light provides a timeline, but to see the architects of reionization, we must look deeper. The quest now is to find the galaxies themselves, the cosmic cities that housed those first generations of stars, shining in the universe's infancy. This means searching for objects at staggering distances, so far that their light has been traveling for over 13 billion years to reach us. In astronomy, such immense distance is measured not in light years but by a concept called redshift. As the universe expands, it stretches the wavelength of light traveling through it. The farther the light has come, the more it is stretched. Light from the earliest epochs is stretched so dramatically that it is shifted completely out of the visible spectrum and into the infrared. For decades, finding these high-redshift galaxies was like trying to spot a specific candle flame from across a vast, foggy continent. Our telescopes simply could not see that faint, stretched infrared light clearly. The frontier of the early universe remained blurred and theoretical. Then, a new eye opened in the void. The James Webb Space Telescope, with its giant gold-coated mirror and suite of exquisitely sensitive infrared instruments, was built for this exact purpose. It is not just another telescope, it is a time machine designed to peer directly into the era of the first light. Since it began its observations, it has been sending back data that is simultaneously exhilarating and deeply puzzling. The telescope has found galaxies at redshifts previously thought improbable, corresponding to a time when the universe was only 200 or 300 million years old. These are not the faint, struggling proto-galaxies many models predicted. They are unexpectedly bright, massive, and seemingly mature. Some appear to have already formed structures like disks, and they contain stars that are not the pure, first-generation population 3 stars, but are already enriched with heavier elements. It is as if archaeologists, expecting to find simple stone tools in the oldest layer of a dig, instead uncovered sophisticated machinery. The brightness and development of these galaxies suggest that star formation in the early cosmos may have been far more efficient and rapid than we ever imagined. Perhaps the first stars formed in incredible, concentrated bursts. Maybe dark matter clumped together more readily, creating deeper gravitational wells that pulled in gas faster. Or perhaps our understanding of how light escapes from these early stellar nurseries needs revision. Each of these brilliant, ancient points of light is now a clue, a challenge to our carefully constructed story of cosmic dawn. They are forcing us to rewrite the opening chapters, reminding us that the universe's first steps out of darkness were not a hesitant shuffle, but a confident, brilliant stride. But how would we recognize one of these first stars if we finally saw it? The answer lies not in its brightness, but in its unique chemical fingerprint, a spectral signature written in pure light. Every star's light, when passed through a prism or a spectrograph, breaks into a rainbow, but that rainbow is not perfect. It is crossed by dark lines where specific colors are missing, absorbed by different elements in the star's outer layers. For a star like our Sun, that spectrum is a complex barcode of absorption lines from iron, calcium, sodium, oxygen, and countless other elements. A true population 3 star, born from pristine gas, would present a spectrum of breathtaking simplicity. Its rainbow would be almost perfectly smooth, devoid of those dark metal lines. The only significant features we might see would be subtle marks from hydrogen and, critically, potentially strong emission lines from helium. This last clue is key. In the fiercely hot, turbulent atmospheres of these massive first stars, the intense radiation can actually excite helium atoms, causing them to glow and add bright lines of specific colors to the spectrum, rather than dark absorption lines. Finding a source with no metal lines and strong helium emission would be the smoking gun, the definitive signature of a star from the dawn of time. It would be a direct window into the universe before chemistry, a beacon of pure creation. The hunt for this spectral ghost is one of the most profound quests in modern astronomy. Researchers are using the James Webb Space Telescope to stare for hundreds of hours into the deepest, darkest patches of sky, collecting every precious photon from the most distant objects. They are not looking for recognizable shapes, but for that specific pattern of light. The challenge is immense. These first stars are likely buried within the earliest, faintest galaxies, their pure light mixed with the glow of later, polluted generations. It is like trying to hear a single, pure note played on a flute within the roar of a full symphony. Yet, the potential reward justifies the search. Capturing that pristine signature would do more than confirm a theory. It would allow us to directly study the physics of the universe's original furnaces. We could measure their temperatures, their masses, and understand the exact conditions that ended the cosmic dark ages. Every faint smudge of light in Webb's deepest images is a candidate, a potential vessel carrying the ancient signature of the very first light. These ancient clues are only pieces of a much larger puzzle, and to assemble the full picture of cosmic dawn, we must turn to the most powerful tools of modern cosmology, the supercomputer simulations that act as our digital time machines. These are not simple animations, but vast, intricate mathematical universes born inside silicon. They begin with the most fundamental starting points we know, the precise initial conditions imprinted in the cosmic microwave background, and then they set in motion the immutable laws of physics. Gravity pulls, gas cools, particles collide, and nuclear fusion ignites, all governed by equations running on millions of processor cores. The goal is breathtakingly ambitious: to grow an entire virtual cosmos from its smooth, hot infancy into the structured, lit universe we see today, and to watch the very first stars be born within it. The simulations must account for everything: the invisible scaffolding of dark matter halos, the flow and chemistry of primordial gas, the blistering radiation from newborn stars, and the explosive feedback from their deaths. They are computational epics, each one a synthetic history that allows us to witness events no telescope could ever capture directly. We can watch a single dark matter halo, a faint ripple in the early universe, slowly gather its cloak of hydrogen gas over hundreds of millions of virtual years. We can zoom in and see the gas within that halo begin to swirl, fragment, and finally ignite into a brilliant, solitary point of light, the first star in its simulated sky. We can then follow the consequences as that star's ultraviolet blaze carves a growing bubble of ionized plasma into the surrounding darkness, and as its catastrophic death scatters newly forged elements back into the void. By running these simulations over and over, tweaking the parameters of physics and the initial conditions, scientists can test which models produce a universe that looks like our own. Do the simulated stars match the expected masses of population 3 behemoths? Does the progress of reionization in the virtual cosmos align with the faint polarization signal we see in the cosmic microwave background? When we compare the simulated galaxies at various ages to the faint, redshifted smudges now being captured by the James Webb Space Telescope, do they share the same brightness, size, and distribution? Every mismatch is a clue pointing either to a flaw in our understanding or to a new, undiscovered piece of cosmic physics. These digital laboratories allow us to experiment with the dawn of time itself, turning the greatest story of our origins into a testable, evolving science. Yet for all the power of our telescopes and simulations, the early universe refuses to be a simple story. Each new observation seems to reveal a deeper layer of mystery, challenging our most cherished models. The James Webb Space Telescope's most startling discovery is not just the existence of early galaxies, but their bewildering abundance and maturity. According to many leading theories of cosmic structure formation, there simply should not have been enough time for dark matter halos to gather so much gas, for that gas to cool and fragment, and for billions of stars to ignite, all within the first few 100 million years. These galaxies are not the faint, struggling embers we predicted. They are brilliant bonfires in the cosmic dawn, shining far too brightly, far too soon. It is as if we opened a history textbook to the chapter on ancient civilizations and found photographs of skyscrapers. This brightness crisis forces astronomers to reconsider fundamental assumptions. Perhaps the very first stars formed with astonishing efficiency, in sudden, violent bursts that flooded their host galaxies with light. Or maybe the early universe found a shortcut, a way to funnel gas into these stellar nurseries at a rate we have not yet accounted for in our physics. Some have even speculated that the initial seeds of structure, those quantum ripples from inflation, might have been slightly larger on small scales than we thought, giving galaxy formation a head start. Each brilliant point of light in Webb's deepest field is now a question mark, a demand for a new chapter in our cosmic storybook. The timeline of reionization itself is another puzzle. We can measure its broad strokes from the cosmic microwave background, but the details are murky. Was it a swift, dramatic event driven by a few titanic early galaxies, or a slow, steady process fueled by countless smaller, fainter ones? The evidence seems to point to a middle path, but it leaves key questions unanswered. What finally provided the last, decisive push of ionizing radiation to finish the job? And how did the first luminous objects manage to carve out such vast, transparent bubbles in the neutral fog so quickly? The physics of spreading ionization fronts through a clumpy, uneven universe is incredibly complex, and our simulations struggle to replicate the precise history we infer from the data. It suggests we might be missing a key player, an additional source of energetic radiation in the early cosmos that helped clear the fog. This leads to one of the most intriguing possibilities in modern cosmology, that the first light might not have come from stars at all. Could there have been alternative beacons in the dark? One compelling hypothesis points to the mysterious substance that makes up most of the universe's matter, dark matter. In some theoretical models, dark matter particles are their own antimatter counterparts. When two such particles collide, they would annihilate each other in a flash of pure energy, releasing gamma rays and other radiation. In the dense cores of the very first dark matter halos, this annihilation could have been intense, potentially heating the primordial gas or even providing a faint, universal glow that preceded the first stars. While this is a speculative idea, it represents the kind of outside-the-box thinking these new puzzles demand. Another radical candidate is the direct collapse black hole. Under certain rare conditions in the early universe, a massive cloud of pure hydrogen might have collapsed so rapidly and with so little fragmentation that it bypassed the star-forming stage entirely, instead condensing directly into a black hole weighing thousands of solar masses. Such an object, greedily consuming the gas around it, would have unleashed a torrent of ultraviolet and X-ray radiation as its meal swirled into an accretion disk, potentially becoming a brilliant, compact beacon that could ionize its surroundings far more efficiently than a cluster of early stars. These exotic possibilities remind us that the universe is under no obligation to follow our simplest narratives. The end of the cosmic dark ages may have been a symphony with many different instruments, some of which we are only beginning to imagine. The sheer brilliance of those first galaxies presents a profound challenge. To shine so brightly so soon, they must have harbored not just stars, but engines of unimaginable power. This leads us to one of the most radical ideas in modern cosmology, that the universe's first light might have come not from a furnace, but from a cosmic vacuum. The theory of direct collapse black holes proposes a shortcut in cosmic evolution. In the dense, pristine cores of the very first giant gas clouds, something extraordinary could have happened. Instead of fragmenting into a cluster of massive stars, the entire cloud, weighing perhaps 100,000 suns or more, might have collapsed in on itself as a single, catastrophic entity. There was no delicate dance of cooling and fragmentation this time. The gas, still pure hydrogen and helium with no dust to help it shed heat, simply grew hotter and denser until its own internal pressure could no longer hold back gravity's final embrace. But it did not ignite a star. The collapse was so rapid and monolithic that it bypassed nuclear fusion entirely. The entire colossal mass plunged past the point of no return, condensing directly into a single, monstrous object, a black hole seed of staggering proportions. This was not the gentle stellar mass black hole left by a supernova. This was a primordial giant born from the womb of the dark ages itself, a gravitational singularity thousands of times the mass of our Sun appearing in the cosmic dawn. Its birth would have been a silent, dark event, but its infancy would light up the cosmos. As this newborn black hole rested at the heart of its gas-rich halo, it began to feed. Vast rivers of primordial hydrogen spiraled into an accretion disk, a swirling maelstrom of matter heated to millions of degrees by friction and gravitational compression. This superheated plasma did not cross the event horizon quietly. It blazed with a ferocious ultraviolet and X-ray glow, a beacon far more efficient at ionizing the surrounding hydrogen than even the hottest population 3 stars. A single direct collapse black hole, actively feeding, could have carved out a titanic bubble of ionized gas, pushing back the neutral fog over a vast region and accelerating the reionization of the entire cosmos. This makes them prime candidates for solving the puzzle of how reionization completed so quickly. They would have been the ultimate early polluters as well, their intense radiation fields potentially triggering complex chemistry in the surrounding gas even before the first supernova enriched it. But their greatest legacy might be what they became. These massive seeds are the most plausible explanation for the supermassive black holes we find at the centers of galaxies today, including the one in our own Milky Way. A stellar mass black hole, even one from a giant star, would need to consume matter at impossible rates for billions of years to grow to millions of solar masses. A direct collapse seed, however, starts with a huge head start. It is like the difference between trying to build a mountain by piling up grains of sand versus starting with a massive boulder and then adding more rock. These primordial giants could have easily grown through mergers and accretion into the gravitational monsters that power the brilliant quasars we see in the early universe. Quasars so luminous they outshine their host galaxies and whose light has traveled nearly 13 billion years to reach us. The existence of such quasars when the universe was less than 1 billion years old is one of astronomy's great timing problems, and direct collapse seeds offer an elegant, if terrifying, solution. The first structures in the cosmos might not have been cradles for stars alone, but also nests for darkness, where the universe learned to build its most efficient engines of light from the purest collapse of gravity itself. The cosmos we inhabit is a testament to that profound transition. It began as a smooth, searing glow, a featureless expanse where no story could be written. Every structure we see today, from the grand sweep of galaxy superclusters to the gentle orbit of a planet around its star, is the direct descendant of a sequence so delicate and interconnected it feels almost miraculous. It was a cosmic domino effect where each step created the necessary conditions for the next. Inflation provided the faintest of blueprints, dark matter built the invisible scaffolding, and molecular hydrogen offered the slow leak of heat that allowed gravity to finally sculpt the gas. The first monstrous stars, burning with a fierce, brief fury, were not an end but a means. Their cataclysmic deaths were the universe's first act of recycling, scattering the ashes of new elements that would cool future gas clouds more efficiently, allowing for smaller, longer-lived stars and eventually the rich chemistry of planets and life. Their brilliant light then acted as a cosmic paintbrush, etching bubbles of transparency into the neutral fog and fundamentally changing the medium of the cosmos itself. This entire epoch, from the first gathering of atoms to the final clearing of the universal haze, established the fundamental architecture for all that would follow. It set the rules for how galaxies assemble, how stars are born and die, and how the raw ingredients for complexity are forged and distributed. We are living in the legacy of that ancient transformation, in a universe that learned how to build itself from darkness into light, from simplicity into a tapestry of breathtaking structure. The era of the first light was not just a beginning, it was a foundation laying down the physical and chemical laws that would guide cosmic evolution for the next 13 billion years. Every new star we see, every galaxy we map, is still following the blueprint written in that long-vanished dawn. The story of cosmic dawn is a testament to a universe in motion, a grand sequence where each event unlocked the next. From the sudden transparency of recombination, through the long, silent gathering of the Dark Ages, to the explosive birth of the first stars and the final clearing of the universal haze, this was a cosmos building its own future. This epoch answers the most profound questions of our existence, revealing how a formless sea of hydrogen and helium could become the rich, structured reality we call home. We are not merely observers of this history, we are its direct product, our very atoms forged in those first stellar furnaces and scattered by their spectacular ends. The darkness was never empty, it was a canvas awaiting the brushstrokes of physics. Our quest to understand it continues to accelerate. Next-generation telescopes, both on the ground and in space, are being designed to listen for the faint radio whisper of neutral hydrogen from the Dark Ages itself, and to capture the light of the very first galaxies with even greater clarity. These instruments will turn the final page of this cosmic prologue, transforming our theoretical understanding into direct observation. To follow these discoveries as they unfold, be sure to subscribe and join us on this ongoing journey into the origins of everything.